merge sort?
You can do whatever you want. What's question 2?
The median question.
Yeah, I mean, you can do whatever you want. Yeah. So did it ask like, oh, yeah, so that was just like median in whatever way you want, right?
Yeah, it has no
Yeah.
how to use sorted or sort.
Yeah, I mean, like bubble sort is probably easier than merge sort, but
Oh, so it's like
I mean, that would be the idea. Yeah.
I thought you were like forced to use bubble sort definition.
I mean, the definition that includes, like the idea you can do whatever you want. So like you can do bubble sort. I think that's what most people did. And then you can also just like check for every element. Is that the median? Is that the median? Is that the median?
Yeah.
So that might be like more, in a way, more straightforward. But you can. I mean, I think like I don't remember if there were any limits on it, but I think you could do like that was supposed to be an easy question, and like you could do whatever you want. Yeah.
Can you check the values are larger or less than that?
Yeah. So you can just go every element and then like, is that the median? No. Okay. Is that the median? Is that the median? Yeah.
Yeah.
Totally.
I feel like this not having better position where greater than 10 minus over 2 and less than 10 minus over 2 at the same time.
All right. Does anyone want any explanation about anything? Yeah.
Yeah, for recursion for question 4 on 2022.
Do you guys do any other exams?
Yeah.
Yeah. Sorry. Well, I'm not as bad as Jim Davis, I think. So yeah. So what's the question?
For question 4, just getting to recursion.
Yeah.
Like how do you have a global?
Yeah. So you would. So basically, like it says, take a list, and return it. So like so like in general, you don't need a global variable. So is global variables? Yeah. So global variables are banned. So what's not banned is we haven't actually, I think, done default variables this year. So what you can do is you can just keep track of what's going on in another parameter. Another thing you can do is you could just advance by 2 every time. So slicing, I think, was not bad, right? So you would say, okay, so if we are at the start of the list, then we take the first one. So that would be L0. And then what we'll do is we'll just advance 3 more. Right? So take the list and it will consist of L at 0 and then every third of starting from element 3. Down the road. And now we need a base case. So basically, if the length of L is less than 3, then we are not quite. So I think we should say if length of L is less than 3, then we just say return the first one, right? So return L at 0. Right. So the idea is how do you print every third of a list? Well, you say whatever, like a long list. So you say, well, take the first one and then do every third of this part. Makes sense?
Return L doing it.
Well, it's just that like every third, like I don't remember if here I asked like the first one. Yeah. Oh, I didn't actually. So because I want like so I don't want like 5, 12. I actually want 7 and so on. Yeah, you're right. So that means that I want to actually so Copilot was correct. So like if it's less than 3, then it's just empty. And then this would not be like L at 0, it would be like the third one. So L at 2, and then starting at 5, I guess. So the difference is before I thought that they asked like 5 and then 12 and then 6. And actually it was like 7 and then I guess 4. So that means that I should start with the third one. So I should start with 7. And then every third of the rest would be every third starting with, is it from 5? So I want 12. So every third starting with the 8, I suppose. Right. So that means that I'm starting at 3, actually. Sorry.
Right. Cool question. We predict the average for this event.
So we went like, I don't know, like it's usually in the 60s, like out of 100.
This one's out of 120.
That doesn't matter. Like, it's like as a percentage, it's like the percentage is usually in the 60s is the answer. And then usually there is an adjustment. So yeah. But like honestly, it doesn't matter. Like you just do your best. The average on the exam is like not actually the important thing. So the important thing is like the average in the course. Yeah. The average in the course is ordinarily between 75 and 80. And then the way I kind of think about, so like there's no way, and like, you know, like you obviously done a lot of exams in your life already and you've done well on them, and you've done some anxiety tests and exams. So like there's no way, like if you look at it, like there's no way to design an exam with like even if you know how the class, like in the abstract, like how good is the class exactly, like this class is a 76 average, this class is 78 average, which you already never do, right? But like let's say that you do, and then like there's no way to design a test that would like aim specifically at the particular average. Like it's always going to be like plus or minus 5 at the very least, right? Like there's just no way to predict exactly. Sometimes like I usually try to kind of predict, and then some of the time I'm getting it like exactly right, but I'm not getting it right on the individual questions. It's just that my mistakes average out in terms of predicting what's going to happen. Not always. But like it doesn't matter. Like there's no objective way to say, okay, like this is like an exam on which the average should be 70 or whatever. So what happens in practice is I give the exam, we grade that. By the way, kind of the grading scheme, the marking scheme has a huge influence on what the average is, right? So that's another factor. That's like not about the exam exactly. It's about how strictly you grade. Yeah. And then, you know, it comes out to whatever it comes out. And then the U of T has kind of the way you're supposed to do it, at least at U of T, like that's the official line, is you say the people who deserve an A plus should get an A plus, the people who deserve an A should get an A down the line. And that's what I try to do, right? So I try to see, okay, like here are the people who, like under whatever adjustment scheme that they come up with, if there is an adjustment, here are the people who are getting a B. Like, would a B is good, A is excellent, C is adequate, whatever, right? Would I describe the people who are currently getting a B as good based on what they see on the exam? And then if the answer is yes, okay, like this is a good adjustment scheme. If the answer is no, I go back to the drawing board and say, okay, like how do we adjust in such a way that the people who would be described as good are getting a B, and the people who are described as excellent are getting an A, and the people who are like particularly excellent are getting an A plus. So that's kind of the best I can do because that's literally what they do. In terms of the exam, like I honestly, I think like 2020 was different. All the other exams, I think if you look at them, well, like you might have kind of definitely like 2015 was like maybe harder than average, but yeah. And then like the averages don't come out exactly the same, but like that's just an artifact of the grading scheme.
I have a question with the agent report. I had tweaked it, I made this error that says like code is not run because
I mean, usually it means you didn't close some kind of bracket.
Oh.
So I'm guessing mine will run. Well, we can try. Yeah, mine is fine. Yeah.
We don't see a question for 2019.
Question 2019.
Oh, wait, no, I think it was 2016. Yeah, 2016. Sorry, it was question 4.
Yeah. Yeah.
Oh, is this?
Oh, this is the metro. Right here, cursor function. So this is max. So basically, what's the max of the list? So one way to kind of decompose this is to say, okay, so, and there are several ways actually. One way is to say, well, the max of a list is either it's the first element or it's not the first element. If it's the first element, then it's greater than the max of the rest of the list. If it's not the first element, then the answer is the max of the rest of the list, right? So you can say something like this. That's actually good. So we're saying if the length is 1, we just return L at 0 because just one element and it's the max. Otherwise, well, it's the larger between L and 0 and the max of the rest of the list.
But
Was max banned or something?
Yeah, max was banned.
Yeah, well, but like this max is easy, right? So you could say like if whatever, like max rest is max rec, and then something like this, right? So like, because like the max of 2 elements is easy.
Yeah.
So another thing you could do is you could say, well, what's the max of a list? It's the max of the first half, or it's the max of the second half. So that's kind of like the merge sort thing, right? So you could say, okay, again, and then max 1 is the max of the first half, and max 2 is the max of the second half. I'm not going to write it like this way because it's ugly, so I'm just going to like return the max. Right, so like the maximum of the entire list is the larger between the maximum of the first half of the list and the maximum of the second half of the list. Is that making sense?
Yeah, just one question. You got like around not using the max by using max rest. Could you like explain that more in depth if possible?
Yeah, I'm just saying kind of like, you know, what's the like in essence, I'm just like writing a code that takes the larger of the 2 elements, right? So I'm just saying like if L at 0 is larger, then I return L at 0. If L at 0 is not larger, then I return max rest. Yeah.
Does it complexity for the second?
No. So well, I mean, so like yes and no, basically. So the thing, so that's actually a good point. So what happens is, let's say you get like a list of length n. So then again, like you go here and so I'll write it as n rather than length of L just because it's easier. So that's like this. And then, so the recursion tree, like you're right, it looks the same. And then the next question is, does every call take the same amount of time? And the answer is, as it happens, no, but for a silly reason, right? So this operation is creating a new list of length n over 2, and creating a new list of length n over 2 does take time that's proportional to n over 2. And this is also creating a list of length n over 2, and that's also time that's proportional to n over 2. So the reasoning is the same, like because of this operation, right? So this takes k times n because you're creating two lists of length n over 2. And then over here, you're creating two lists of length n over 4, another two lists of length n over 4. So that also takes kn. And then like it's the same reasoning again for every level on the whole takes time that's proportional to n. And there's a log n levels. So yes, n log n. But it's for like a silly reason, right? Because like we're creating here a new copy of a list, which we did not really have to do. All we need like is half the list. And in fact, you can make it faster by saying I am gonna keep just passing the list around, and instead of passing half the list, I'll say kind of I and j. So this would be, yes. So this would be like this. And here I'll say, okay, so if I is equal to j, then the maximum of from I up to j inclusive of j is just L at I, which is the same as L at j. And otherwise I'll say, okay, like the rest of the list is, I want to do halves. So the max of the first half is going to be like this, and the max of the second half, max 2, is going to be like this, right? So I'm saying I want the max between I and j, and max 1 is the max between I and halfway through I to j, and then the second half is I to j through to j.
J is makeup of this, sorry.
Say it?
Is J?
No, I and j are indices, right? So we're possibly like you're dividing the list into like 1/16 parts of the list, and then like taking what's the max of the first 1/16, what the max of the second 1/16, and so on. And then you're collating that, and eventually you're getting the result. Right. So this is kind of getting a little bit into the weeds, but yes, like you can do it like this. And then whatever, I'll just do like max of max 1, max 2, right? And then over here, like the n in this case is going to be like j minus I plus 1, right? So initially you start with just the whole thing. So I is 0 and j is length of L minus 1. And then here, like again, like you are sending in half the range of I to j and the other half the range of I to j. So that will look the same. However, each call now really takes the same amount of time because you're not doing any work here. You're just calling max rec fast. And you're taking max of 2 integers, which is really fast. Make sense? So that means that here you have 1 call, and here you have 2 calls, and then you have 4 calls, and so on, up to 2 to the power of log 2n. Right? Because you have log 2n steps between j minus I plus 1 being n and j minus I plus 1 being just 0. No, 1. And are you with me? So that means that the total amount of calls is, so what Copilot knows, is, yeah, 2n minus. So this way, which is essentially the same thing, is O of n. So by the way, how are you liking the lecturing with Copilot? Is that like too fast? And like, would you rather that I type everything myself or? So like that's yeah, like that's something that I obviously like I have VS Code with Copilot like the whole time. I just type everything in ISO because I think that's useful. But like in 190, I'm probably moving on to like this is a little bit like slides, right? So yeah.
I'm still trying to go over like the concept where you determine that like it's log 2 of n as a depth.
Yeah, well, because like I just ask, like I start with n, and then the next level is n over 2, and then the next level is n over 4, and so on. So I'm asking like, how many levels do I need in order to get to just 1 where I stop? And that's log 2n. And that's just because like, like if you go like 1, 2, 4, 8, whatever, like this, and you ask like how many steps to 1024, that's like asking like what power do I need to raise 2, because like this is like 2 to the 0 and then 2 to the 1 and so on up to 2 to the k. And I'm basically asking what's k if 2 to the k is 1024, and then the answer is yeah. And here, like the only thing is like I'm going backwards usually, right? So I'm starting with n and then I'm going down to 1 rather than starting from 1 and going up to n, but that's the same. Yeah.
On the same question, question 4. I wrote something that worked,
Okay.
but I don't understand how.
Yeah.
So could you explain me what it will come to
yeah. Yeah. Did you grade yourself as 5 out of 5? Yeah. Yeah. So at my PUI placement, we had like a whiteboard with like quotes from the people who worked at the office. My favorite quote. So my favorite quote there was, "It works, but it works, but it doesn't compile." And the joke would be like usually compile means like the code passes like the basic, well, a little bit more common, but the code passes the basic checks. So like usually the situation is like it compiles, but like when it runs, it doesn't work. So it's like it works, but it doesn't compile. It's like amazing. So I think that's like your situation. So, kind of, a little bit. So you're saying max rec, so I'll just copy that if that's okay. So you're saying, so I'll think through it as I'm doing it. So you're saying max is L at 0, and you're saying if max is smaller than L1, return max rec L from 1, and then you're saying else, and then you're saying if length of L is equal to 2, well, return max, else return max rec L at 0 plus, so I'm just writing it down, and now I'll think about it.
I'll make sure it works.
Yeah, well, let's think about it. So, okay. So the first thing I would do, and like maybe that's useful, like in terms of like thinking about it, like you wrote something on paper and you're just thinking about like, does it work? So the first thing I'll do is I'll check, okay, like base case, this base case seems fine. And then you're saying max is L at 0, and you're saying if max is smaller than L at 1, you are which is L at 0. You are returning max rec L1. And I would ask, okay, like, is this mathematically correct? And I would say, well, yes, like if L at 0 is smaller than L at 1, L at 0 is definitely not the maximum. So I would not call it the maximum, given that it's possibly not. And like that's definitely correct. And that's good in the sense that you're making progress because you've shortened the list and eventually it'll get shorter and shorter. So yeah, so that part is good. Now you're saying, okay, suppose it's not. So then you're saying if length of L is equal to 2, return max. So here you're saying if L at 0 is larger than L at 1 or equal, I suppose, then return L at 0. Yes, that's correct. Else you're saying, okay, so L at 0 is larger than L at 1. I'm leaving out L at 1 because it's definitely not the maximum. And I'm creating this new list, which is L without L at 1. And I'll find the maximum of that. And I would say, yes, like, yeah, that works. And I would say the reason that works is you are either returning an answer or you're shortening the list in a way that's mathematically correct. So, well, because you're saying L at 1 is definitely not the maximum. So if L would be kind of like that, right? So L would be kind of like that. It's like 5, 2, and then whatever, 3, 10, 5, 1, 6. Right. And then so the else here is in a situation where 5 is greater than 2. So L at 0 is greater than L at 1. So the 2 is definitely not the maximum because L at 0 is larger. So this guy, not the maximum. And what you're saying is just take this guy out and return whatever the maximum of this is. Which is, yeah, like that's good. You're making progress. You removed one of the elements.
The next step will then remove the 3.
Yeah, so then you would say, well, is L at 0 greater than 3? The answer is yes, so leave this out. Well, so usually we do it the other way. Let me do it kind of like the way we usually do from the bottom up rather than the top down. No, just convention. I mean, like in a way, like okay, like trees are kind of this way rather than this way, I suppose. But yeah, like that's not my goal is this chain. So you're doing this. But yeah, no, totally. Like you can also look at it like that, and then it's gonna be the other. So I mean, like you like that, like I'm doing it the way people usually do it, but like it honestly doesn't matter. So yeah, so the next call, so you're asking, is L at 0 greater than L at 1? Yes, so the 3 goes. The next time, so now you're at 5, 10, 2, so not the case. And then you're saying here, if max is smaller than L at 1, which it is, so if 5 is smaller than 10, then you're saying, give me the max of this guy. And the next time you're getting here. So your return 10.
Would you ask to analyze this?
I mean, John just made this up.
You just made this up right now, or not right now? But I couldn't understand why it's created.
But is this good now?
Kind of.
Well, so like the way I would approach it again, kind of. So this has its limits because like it's hard to kind of hold everything in your mind at the same time. I would say in this kind of like this is like a little bit convoluted, but like you just say, okay, like so like maybe this will help. So going back to kind of like the easiest example, right? So like a to the n, I'm just kind of going through the reasoning here. So like a to the n is like this. This is just like mathematically correct. And then that just translates to this kind of code, right? Where you're saying, well, like because a to the n is a times a to the n minus 1, well, we'll just return a times a to the n minus 1. And that's got to be correct. So in the same way, like to think about this, like let me rewrite this a little bit because like I think part of it is that this is just a little convoluted. But the basic idea is if well, like the base case you should keep, right? And then you're saying, okay, so like if L at 0 is greater than L at 1, then we leave out L at 1 because it's definitely not the maximum. Otherwise, we leave out L at 0 because L at 0 is definitely not the maximum. And this is just like mathematically correct, right? So like in the same way that leaving out that kind of a to the n is equal to a to the n minus 1 times a, the maximum of a list is either the maximum of the rest of the list if L at 0 is definitely not the maximum, or the maximum of the list without L at 1 if L at 1 is definitely not the maximum. No? And like you see that this is like the same, right? It's just like, yeah.
I put the function in the if statement, that will also work, right?
Say it.
I checked if L0 is greater than max, right? Just myself the first number.
Yeah, I mean that's more like the previous approach, but yeah.
Oh, how do you analyze the time complexity of
Like this one. So this one again, kind of it's like n squared, but for an annoying reason. So basically, this step takes time, and like this one as well takes time that's proportional to n minus 1 because you're creating a new list that's of length n minus 1. Yeah, I mean, it's the same. Like I was slicing the original as well. Oh yeah, it's n squared. Yeah, it's n squared. Yeah, and it's n squared because like what's happening, like it doesn't matter if so it's like always the same. But let's say for simplicity that this always happens. So what happens is you have like time that's proportional to n minus 1, so like kn minus 1, and then you make the call to a list that's one shorter, so the next time it's k times n minus 2, and then and so on. So that's like this, and this is like this, and this is indeed like this. So yeah, and that's.
I don't know if someone else already asked this, but can we review the algorithm the last year's like 6 question? The one where the person calls. I remember following it.
Which one? Oh, 2022, I guess.
Sorry, 6. Question 6, letter C.
Which year?
2022.
Yeah.
I remember following it looks the way
Wait, sorry. Oh, that's the midterm.
to the solutions.
This one?
So,
Yeah.
Yeah, so it,
Oh, yeah. Okay.
so what was the last one? Is this purposely a very hard question or is this?
Yeah.
Okay, yeah, that makes sense. And so I followed the part where we were doing like a geometric series number of calls.
Yeah,
At least in what, did you write the solution there?
I did. Yeah.
Okay.
Yeah.
It's just then a step when we go. I'm just worried how to get like essentially the second.
U6. Wait. Oh, that's the midterm again. Sorry.
Yeah.
Yeah.
for me, it makes sense since we're counting by level, we have 1 call, 3 calls, that's great.
Yeah.
And that seems great.
Yeah.
And so we have log base 2n calls.
Yeah.
I'm a little confused about plus term, but that shouldn't be a problem. And so then how do you think that's a thing that is to the log base 2n? Like where's that to the log base 2n?
This is just, you mean like this one?
No, it's on the same line up there.
Sorry, so which here? Oh, this one?
Yeah, how do you transform what you had before? Where does
Yeah, so let me see what's written here. So log 2n plus 2 levels. So wait, so this is like this is like the usual, this is like the usual thing, right? So this is just n, right? And then the next one is, no, it's 2. So yes, the next one is wait, did I oh sorry, so the -1 here is not correct. Like the -1 should be outside. Yeah. Yeah, sorry about that. Yeah, so this is like n, and this is n over 2, and so on. Yeah.
Where are we thinking this in this? You see what I'm saying? Because it seems to be useful later, but I'm just confused.
Yeah, sorry, let me like review, let me review what I'm doing here. So like the log 2n, like the log 2n levels is like just the same as the usual thing where, yeah, where you go like n over 2, n over 4, and so on up to 0 in this case. So how many levels is that? Well, approximately log 2n. So like that's all I'm saying.
So binary search.
Yeah, like anything where you go n over 2, n over 4. Yeah, so that's like the usual. That's all I'm saying here. Like I shouldn't, like the -1. Sorry about that. But yeah.
Okay.
So like that's all I'm saying. And then I'm saying, okay, so this is how many levels, and then the first level has 1, and the second level has 3 to the 1, because the second level has 3. And then the next level has 9, and so on. And we're going up to approximately log 2n.
Yeah.
So that is the geometric series.
Log base 2n
as the number of terms.
Okay, which was, I think, in our old formula, it was n or something.
That's correct. Yes.
All right.
Yeah. So now we're here, and that was actually enough for full marks.
Okay.
But
well, because then the rest is like, oh, then it's proportional, and then anything else you're doing, you remove.
Well, so the difficulty here, sorry, this was yeah. So the difficulty here is like, so if you have like log 2n as just a term, that's just proportional to log n. The base doesn't matter. But that's not, like n squared is not the same as n cubed, even though like 2 and 3 are constants, right? So like if it's in the exponent, it's not the same. So here I'm just doing some algebra to transform it.
Yeah, that
yeah.
was just sort of algebra.
Yeah.
Okay. So at the end of the day, is it all I'm doing is all you're doing there is this is the number of calls. For each call, there's this number of, this is the number of levels.
Yeah.
Based on n. Based on
yeah.
For each of these levels, there's this many calls. Multiply that. Go into the geometric simple.
Yeah.
All right. Okay.
Yeah, and then like it's nice that it comes out to be n to the power of 1.6, but
yeah.
But that's just like a funny thing.
What's some crazy ones there? Because it seems like most of the ones we've been seeing are n squared.
Yeah.
Like linear,
yeah.
Something more crazy than this.
Nothing that you've well, like you've seen this, but like yeah. Okay. So this. Like with the tools of this course, this looks a little bit crazy. In principle, like there is like a general method to do it. It's called like the master theorem, because it's general. But like that's but that's like not something that we've done, and that wasn't like nobody did that on the exam either. The intention was that you just do it from first principles, as one does in exam. barely anyone did, to be honest. I think the average of this question was like 5% or something.
Can you use Russell?
Say it?
Can you use Russell?
I mean, if you knew it, yeah. Like that wasn't the intention and nobody did, but yeah, like as it happens.
Can you go over how, one of the trees when it's like n log n? And then
Yeah.
when you're like summing up the terms, like what are you taking this?
Yeah. Well, so like we actually had an example of analog n like recently, right? So that was like the bad max, right? Wait, did I erase it? No. That's like the fast one. Oh, I kind of hand waved it. Yeah, okay. So like here it is, right? So we're saying, okay, we are starting with a list of length n. So here, like it's the length of the list. And then here we're making two calls. So one to a list of length n over 2 and another to a list of length n over 2, right? Because like you're making this call and you're making this call. And then from here, you're making, again, two calls, n over 4, n over 4. And so on, up until the point where you get to the ones. Right? So here, in order to create a new list that's of length n over 2, you need to do work that's proportional to n over 2, because like you need to put n over 2 numbers in memory. The work that needs to be done there is proportional to n over 2. Right, so that's like because of this operation, which we could actually fix by just passing the indices around. Does that make sense? So yeah, so okay, so here on this level in total we do work that's proportional to n, so like k times n. And then on this level, what happens is in this call, like you're calling it on the first half of L, and you're saying, well, like do the first quarter and the second quarter and compare the maxima for the first and second quarters. And then for this one, you also do that. So you say third quarter and fourth quarter, compare the maximum. So in total, what you're doing here is you're creating two quarters, and then over here, you're also creating two quarters. So one quarter, another quarter in one call, third quarter, fourth quarter in another call. So in total, you are doing 4 quarters of L, which is the same as L, right? So over here, you're also doing work that's proportional to it. If you consider the 2 quarters created here and the 2 quarters created here. And then here you have 4 quarters, and out of those, you're creating 2/8 each, 2/8 each. So that's 8/8. So that's, again, work that's proportional to k times n. And that's how it goes. Well, like not on this level, actually. Oh, yes, on this level. So on this level, like for each call, you're doing like one piece of work, but there's n calls. So on each level, you're doing work that's k times n. If you take both of them, like the whole of the level, right? And then you're saying log to n levels. So O of n log n in total, because k times n times log to n. Because you're going from n to n over 2 to n over 4 to n over 8 and so on down to 1, and you ask how many steps does it take to go from n to 1 if you're dividing by 2 every time, and the answer is log to n approximately.
So is that like, is k, when I put the variable k, is that the number of?
No, k is just a constant, right? So like I need to say like I'm doing like work that's proportional to n. I need to like some way of writing it.
Yeah, one quick question. If let's say you commented out max, you didn't call it, then it would just be log n, right?
Say it.
If you did, because in this case, it's you're calling max one and then max two, and that's
Yeah.
why it's n log n. If you just called max one, it would just be log two, correct?
If no, so like at the very least, like you doing it once, you're already doing work that's proportional to n because you're creating a list of length n over 2.
Okay.
So that's like at the very least it's at the very least it's O of n.
Okay.
So like it's an interesting question. So like let's say you do this and you just say return, well. Sorry, did that answer your question?
Yeah.
Okay, so let's say that you say like return just max, well, like that's in fact like the other way of doing it, right? Like, and we're doing a little bit of extra work here, and then, well, actually, that's not what you're asking. Like, you're asking like something silly. So, not the question is silly. It's like the function that results in is kind of silly, right? So you're just saying like return this, right? So then, well, what is it going to be? Well, it's n, and then n over 2, and then n over 4, and so on. And so, and this is this is log to n levels. So this is going to be O of n. So what it is you could say it as the other way. So like 2 to the 0, so O of it times k. So 2 to the 0 plus 2 to the 1 plus and so on up to n. So this is plus 2 to the log to n because that's n. And then that's the geometric series. Well, what are you saying? That is not locked. And then this is the geometric series. That works out to n minus 1. So O of n. I know why Copilot insists it's n log n. It's wrong. So O of n. Yeah.
So geometric series, are you adding how many calls per each
in this, no, so the number of calls is log to n. It's just that in each call I do work that's proportional to the length of the input list because I'm creating this list of length n over 2.
If there were like 3 calls per level, then would it be calls per n?
So 3 calls per level is this question, I think, is what you're asking. And the answer, like, that's like the complicated one.
Okay. And also with the last one you did, and it's just like going like straight up and like n and then just n4.
Yeah.
Why is that not this O log n? Why
So the number of calls is O log n. However, it's not the case that each call takes the same amount of time. And the reason for that is this guy. So this guy is creating a new list that's of length of L over 2. And that takes work that's proportional to n over 2. So if the list is shorter, then there's less work. If the list is longer, there's more work. So you can't just count calls. You need to actually account for the work that's done in each call because it's different. That's right. Yeah. So we had one of those. Yeah. Yeah. So it's like this is the one. Well, it turns out to be all of that. So, and there, like, it's like a complicated reason that it turns out to be O of n. It's like you're adding n plus n over 2 plus n over 4 and so on. And it turns out that this is equal to 2n approximately.
The values you're adding, where do you?
Say?
The values that you're adding, where do you?
So this is like the amount of work in the first call because you're giving the full list is proportional to n. That's the full list. And then you're giving us half the list. So the amount of work is proportional to n over 2. Then you give it half that, so the amount of work is proportional to n over 4. And then the total amount of work is all of that added up.
Okay.
Yeah.
Do you multiply by k because each iteration takes like a slicing?
No, like multiply by k just because I'm saying the amount of work is proportional to n. It's not like literally that it's n seconds. It's k times n seconds for some constant k.
Another question, so for when you had like max 1 and max 2, each one took like L over 2, right?
That's right.
But you had two of them, so they would add.
That's exactly right. Yeah, so this is this, yeah.
And is that why like I just don't understand why there's like it's K multiplied by n on each level, because like I like usually see like the depth is like log n. Is that-
Well, that's the depth. And then we're not looking like up, down, up to down, down to up. We're looking left to right. So we're asking on this level, so like for this code where it's the full list, what is the runtime proportional to? And the answer is K times n, because, well, you need to do work that's proportional to the length of L. And then we're saying on this level, the total amount of work, what is it? And the answer is, I think you said, right? So like here, it's proportional to n over 2, and then here it's also proportional to n over 2. Add that together, and that turns out to also be K times n, because it's K times n over 2 plus K times n over 2. And then this is like 4 times K times n over 4. So again, K times n. So it's like, it's a trick, right? So you're saying, I can't add up all the time that it takes to do the individual calls because I know how to do that. But if I group them together, it turns out that I can just say like this group, which is just one call, is K times n, and then this group taken together is also K times n, and so on.
Last question. So how would this differ from something that just had a log space to it? Like for example, like, yeah, like a search that only split them into 2 but didn't slice through. Like it wouldn't be like.
Are you asking about this guy? I think we had, so wait, yeah, like you're asking about like this guy, right?
Yes. So my question is like, if you split it in half each time and you
Yeah.
don't do slicing on each iteration.
You don't, if you don't want to do slicing,
Yeah.
well, like if you don't do slicing, so like you do something with the indices, then yeah, like log to n calls, and like if you don't do slicing, then each call takes the same amount of time. So if that's the case and there is log to n calls, then it's all log n. Yeah. Yeah.
When dividing the complexity, do we have to include the 2 or can we drop it?
I mean, I would not penalize you. Well, I mean, like I'm asking for like the simplest form, so like it's better to drop the 2 just kind of to make it like as simple as possible. I would not penalize people for not dropping the 2. But like in a way, kind of like you drop the 2, it's kind of, well, depending on the notation, it's like log 10 or log e. And like either is fine because they're all proportional to each other.
You make that last year's final question, that one is.
Yeah.
As just like a math problem in itself, that's.
Well, yeah, so like like I said, I think I said on like either Discord and Piazza, we haven't really, like, you have all the tools, but we haven't really done kind of an example that's like a similar approach this year, if that's what you're asking.
This almost seems like a common.
Yeah, well, like, well, I mean, like, that's an interesting thing, because I thought about it like that, right? Like I thought about, so like we just haven't done, we haven't gotten to doing kind of all passwords of arbitrary length, I think, with recursion. And this is kind of like a similar thing, right? So so we're talking about the last question. Wait, did they just have 7 last year? Okay. So basically one way to approach this question is to say, well, like we will think about all the possible friendship chains, and for each friendship chain, we'll check, is that one the longest? And last year, we actually had a similar thing where we generated all the passwords of arbitrary length, which is kind of the same, right? It's like, instead of taking like all sequences of characters in arbitrary combination, you're taking all the combinations of friends. And that was kind of like a preset thing that people had last year that you don't have this year because you haven't done this example. And then you would kind of guess and check. As it turns out, for this particular problem, you actually don't like that approach takes a long time. Like there's a lot of possible chains. As it turns out, for this one, there's like an open cubed algorithm that you can also do, which some people actually manage to. So, and that one like is not a combinatoric. So like it's possible.
You can even say like, well, I know it's about, at least for this one, I know it's about less than 6. So that already means like you can have a friendship chain longer than 6 people, there's only 6 people on this list.
Sure.
So then, I don't know.
I mean, like this is just like a sample input, right? Like you,
Yeah, I can do that, but I'm saying, I really wanted a very cool one that could just say, how many unique people are there? And then return that number, and it wouldn't always be right. It might be kind of- if I was trying to write something in 2 minutes, I'm saying that's whatever.
I
If you know
mean,
what I'm saying.
I mean, I don't think that would earn you any
Yeah.
points, but like return 42 on anything. Sometimes it's right. Yeah,
But my friend said like this question, you could do it with like depth first search.
yeah.
Is that like, what does that have to do with?
Long story. So let's leave it to 190. Like that's like I can't do it like so that's like an hour.
2015 question 9.
Sorry, let me take sorry, did you have a question? Or yeah, just I'm just alternating between different people. That's okay. Yeah.
I'm gonna ask about this one. It was just, I just had an idea if we could like figure out the longest list.
Yeah.
And then figure out the person, each person put their list into that.
Yeah.
And then try to find like the longest chain that goes down.
Yeah, you could do it, yeah. So that would still be like kind of equivalent to just trying all the sequences. But yeah, like if you want to think about it, I don't recommend thinking about it today. But if you want to think about it, I would recommend like the easiest thing, I think, the easiest approach, I think, is like looking at how to generate all possible strings of a certain length with recursion, and we'll do it in 190. And then just out of that, just generate all the possible kind of chains of friends and just check like, is that an actual chain? Is that an actual chain? Is that an actual chain? And then see which one is the longest. Like that's like the official solution. Yeah.
I have a question about one of the ones from 2015.
Mhm.
It's for question 2. And we did like sparse matrices this year with the
Yeah.
sparse vectors, and I was just wondering if you could explain.
I mean, we have done sparse vectors technically in project 3, right? So here, like, so I mean, like, and basically, like, what's a like from ESC180, like, what's a vector? It's just like a matrix with like number of rows equals to 1, right? Or whatever. So like you just say, okay, like so like something like this, you're saying, okay, like in the first coordinate, I guess we're doing based 1. So in the first coordinates, it's 4, and then at the second coordinate, it's 5, and then at the fourth coordinate, it's 10, and then everything else is 0. So does this part make sense?
But isn't it saying that like 1, 4 would be like the coordinate?
No, it's saying like at location 1, so at coordinate 1, the entry is 4.
Okay, so like does it have like an X and Y on the coordinate?
Well, it's like it's a vector, so like it just has like location 1, location 2, location 3, location 4. You could think about it that way. Yeah, so like we're just saying like at coordinate 1 it's a 4, at coordinate 2 it's a 5, at coordinate 4 it's a 10, and everything else is 0.
Okay, so is this explaining one vector, or is that?
Yes. That is like one vector. So like this is stored like this. And then you're saying like, let's say we have 2 vectors like this. So let me do like another one. So let's say that you have like whatever, like 0, 1, 0, 0, 3. So how would that be stored? So at location 2, it's 1, and at location 5, it's 3. Does that make sense?
Yeah.
And then you want the Euclidean distance, so like 4 minus 0 squared plus 5 minus 1 squared plus 0 minus 0 squared plus 10 minus 0 squared plus 0 minus 3 squared. Right. So okay. So so what we need to do is we just want to go. So we want to go through. And that's like a lame way to do it. So we want to go through all the coordinates. So what do I mean by all? So what do I mean by all the coordinates? Like I want. So like if both are 0, then I don't care. But if either one or both are non-zero, then I care. So I can just say so this is so the set thing we haven't like officially done. So this is like the shortest way to do it. So I'll do it without the set in a second. So here I'm just getting the keys of V1 and I'm getting the keys of V2. And then I want to stick them together. So I'm converting them to a list and then I'm sticking the two lists together. And then I might have repetitions. Repetitions would be bad because I don't want to add 5 minus 1 squared twice. Right. So set just makes it so that I just have every element once. Does that make sense? And then I'm saying, okay, so like for every non-zero key, I'll get either a 0 if that's what's available, or the actual element from V1, and the same for V2, and then I'll add the square difference. So what that would do is the keys would be, so 1, 2, not 3, 4, 5, because those are like the non-zero ones for either one. And then I just go through 1, like, is there a value in V1? Yes, it's 4. There's no value in V2, so I'll just get a 0 by default. That's what get does, right? So it gets like the value at K if there is such a value, or 0 otherwise. And I'll do like 4 minus 0 because I'll get the 0 from V2 using .get, and then 5 minus 1, and then this would not happen because I don't have a key of 3. And then this would happen, and then this would happen. So like if you didn't have list, like there's like multiple things you could do. So I guess like one thing you could do is just do it the slow way. So like if it's like sparse vectors, that's not nice, but maybe that's like the most intuitive, is just like get the maximum key. Because you know its coordinates. So you'll just say this, right? So like go through all the keys. So get the maximum of the keys and go from 1 up to the maximum of the keys, and then add the square difference. Right, so that is potentially slow. If the vectors are sparse, then most of the values that you'll get are just zeros, and 0 minus 0 doesn't make a difference. But you could do it. Maybe that's like more intuitive.
Safely, in this case, if we take a look at questions.
Oh my God. So So forward step of the Gaussian elimination algorithm. So what is the forward step of the Gaussian elimination algorithm? So like you have like a matrix. The Copilot is going to help me out here. Yeah, that's good. Wow, that looks like diagonal, so that's not good. Whatever. Help me out here. Okay, sure. So we have a matrix like this, right? So what does the forward step do? So the forward step says, okay, so take this row and eliminate this guy and this guy. And then take this row and in this case just eliminate this guy. And then potentially, so it's just refusing to give me nice matrices. Why does it want zeros? So like something like that. Just like zeros for some reason. Okay, zeros, fine, right? So okay. So how much work is it? So like you can look at your implementation or like someone else's implementation and you'll see kind of like the nested loop structure. But I just want to look conceptually and say, like, how much is it going to take? So basically what you need to do is, so you need to take, so if, is the matrix n by m or just n by n? M by n, yeah. So what you need to do here is you need to subtract m elements from other sets of m elements n times, right? So elimination of column 1 is k times m times n, right? And that's because we need to subtract m elements n times, right? And then what about elimination of column 2? Not correct. So here, so column 1, that's not correct. We'll fix it in a second. So column 1, that's already eliminated. So now what you want to do is you are at column 2 and you're saying subtract this guy from this guy times a constant, and then subtract this guy times a constant times this guy. Yeah, so m minus 1 and minus 1. And then yes. All right. And so is that figuring it out? It's really not figuring it out. Okay. So that's like that. So forget the k goes and so on. Right? So the k goes outside. And then this is like n times m plus n minus 1 times n minus 1 plus n minus 2 times n minus 2 and so on. And that's kind of basically as far as you need it to go. So in the case that n is equal to m, so if it's a square matrix, this would be like this. And that is like this. And for that, there is, like, it happens that there is a formula, and Gaussian elimination is O n cubed.
Yeah.
And so that obviously kind of n was not equal to m, so you couldn't even do this formula. So like,
Like that's like multivariate.
yeah. Yeah.
Squares.
Say it?
Like if it's a square, you just assume it's a square matrix. That's like
Well, no, like the answer was it's n times m. So like the expectation was kind of like this.
so. But what would the answer be?
You're done.
Sorry.
Like there's not like a very nice formula here.
Okay. So what we're expecting to say on the exam.
Yeah, I mean, like you do the simplest form. Sometimes the simplest form is not that simple.
The super form is.
Yeah. So like it's conceivable that you could like simplify it, but yeah, this is not actually correct. So yeah, like that's. Say again? That. No, like line 30.
Yes. Okay. In the solutions, it said that it's x squared times n.
And square. Well, yeah. So like, I guess you could. Wait, square times that. Yeah. Well, like you could derive, but like this is good enough. Yeah.
I guess you could like, yeah, you could.
Yeah, like you could, but yeah, like you could, and then so here, like you have to fudge it a little bit. So like basically you say this is like smaller or equal than this. Well, that's a little bit much. So basically, like keep the n minus 1 and so on, but make the m be constant.
Oh. And that's a summation of all of that.
Yeah. Like specifically Gaussian elimination, we're done.
Or like in terms of like analyzing algorithms.
Oh, yeah.
It's called.
Yeah. Yeah.
We're gonna keep doing this.
Oh yeah. Oh yeah.
As it is called computer structures.
Yeah. Well, I mean, like the course title is not the boss of me, but yes,
Yeah.
we're gonna be good. Yeah. So and Dean Yip does not keep track, but
But if we, as far as we're gonna do this, and then we add in like memory.
memory, you mean like space complexity?
Yeah, how much space?
Yeah, I think we're gonna mention it a little bit, but like not not really that much. I mean, well, I mean, like I would say kind of about half the course, even more, is just learning C.
It's just like.
And then the other part is kind of like looking at specific problems to which it happens that there is a solution. I guess like the Gaussian elimination is like a good example of like a difficult problem, like solve a system of linear equations to which there happens to be a solution that's sufficient. And we're going to look at kind of those kinds of situations where there is an efficient solution, specifically with an emphasis actually on data structures. So for example, like how do you efficiently make a dictionary? Like that's in fact like a week of ESC180 is like let's actually, yeah, exactly, like let's make a dictionary. Yeah. So like you can look like if you Google like ESC190, like they're like we made notes last year that they're like quite comprehensive actually. So you can look at exact. So like I went a little bit slower this year in ESC180 for one reason or another. So we're gonna like do a little bit of like, well, what used to be 180, I guess, like a week or something, and then we'll just do kind of 190. I mean, don't really plan to change it all that much. So just like Yusef, so like Yusef Rashad is like the TA who kind of worked on making the notes. So like if you Google like Yusef ESC190, that should come up. Yeah.
Can we go over question 7?
2016 question 7. Don't have a good feeling about it. Is that the last? Oh, that's not the last question. That's maybe easy. Question 7. Oh, like all of it?
Like the first 3.
Well, so this one we've done today already. So this one, like what's happening here? So we're saying for I in range n, and then for j in range I over 2, and then we're just doing something, right? So how many times does this repeat? Well, the first time around, this repeats 0 times. Then it repeats actually again 0 times. Then it repeats once and then once. So let me copy. So I equals 0, 0 times. And then I equals 1, 0 times. I equal 2, once, 3, once, 4 twice, 5 twice. And so on. Right? So what's the total number of times that it repeats? Well, it's like 1 plus 1 plus 2 plus 2. Sure. And that equals to 2 times 1 plus 2 plus 3 plus 4 plus 5 up to, well, n over 2. Right? Because like the last time it's approximately n. And this is just the arithmetic series. So is that making sense?
Yeah.
So yeah, just count how many times does this repeat? And then it repeats like approximately like I over 2 times. In fact, like this is integer division, so it's like exactly 0 times twice, because like 0 over 2 and 1 over 2 are both 0. And then 2 over 2 and 3 over 2 are both 1, and so on. So that's the total number of times that it repeats, up to n over 2 plus n over 2. So this is like this. And then like 1 plus 2 plus 3 plus 4 plus 5 and so on. It's quadratic in n over 2. So that's why it's O n squared, basically. So like this is just like details. Does that make sense? So O n squared. Okay. And then like this is an annoying one. Like it's, so I did it, like I think I actually did it like yesterday, but okay. Yeah, like I'll refer you to like the recording of yesterday where I did it twice. I mean it was exactly this one. Oh, sorry. Yeah. Oh, sorry. This is not the annoying one. So this one is just, yeah, okay, sorry. Yeah, I thought this was the annoying one. The annoying one is from another exam. So this one is just like you go from 0 to n cubed, and you do it in steps of n. So this thing repeats n squared times. And then a trick here is that this happens once. So this runs n times the once, and then j never resets. So this guy runs the once in time proportional to n, and then this whole deal runs n squared times, where most of the time this is just proportional, this is just constant.
I don't understand the second part. Why runs there?
Well, because you're going 0, n, 2n, 3n, 4n, and so on up to n cubed. So how many steps to go from 0 to n cubed in steps of n cubed divided by n?
Yes, that was.
Yeah, is that good with everyone?
Why would you say it runs at n squared?
Well, because like we start with I equals 1, and we go up to n cubed in steps of n. Right? So that means like you go, yeah, okay.
When we talk about what's in that,
Yeah.
Is it because like the second one is constant?
It's because the second loop just runs the once. Right, and it runs the once because j never resets to 0. Or the third one is O of n. So this is like one of the things that we've done. Let's look at that. Yeah. So this is like this guy. Sorry, so people probably haven't seen. So this is the third one. So the pattern is every call takes the same amount of time, and you go from n to 2 calls to n over 2 to 4 calls to n over 4, and so on. And the tree looks kind of like this. So you start with n, and then 2 calls to n over 2, 4 calls to n over 4, and so on, log to n levels. So this is like 1 plus 2 plus 4 plus 8, and then up to n, which we like rewrite as 2 to the power of log to n.
Serious, and then like a lot of thing, and then you come back to
Well, I mean, so this is like 2 to the power of log to n plus 1 minus 1 divided by 2 minus 1. 2 to the power of log to n is like you're back to n. So O log n would be this kind of situation. If you go from n to n over 2 to n over 4, like in a recursive situation, and then each call takes the same amount of times. Yeah. Well, so the basic idea, it's like the same, it's like a more complicated version of the raised to 21 game that we did in class, right? So you're saying, what does it mean that X can win? X can win. So X can win means that not cannot win and cannot draw. Right. So that's kind of the basic of what you're saying. Where's my So what is X can win? Well, like if X already won, then that's definitely true, right? So that's this base case. And then we're saying if not wins. So the way we figure out if not wins is we like invert the board. So it's like as if so like basically like X won except on the inverted board. So that means that not won. So that's false. If nobody won and the board is full, then X cannot win because it's a draw. And then we're saying try every possible location and put an X there and say if not will lose with this configuration, then we return true. Right? So just logically, we're saying try to put an X in every location, and then if it's now not's turn and it will lose, then that means that X won. So the reason this is useful is like we're progressing, right? So like we're filling up the board every time. So we're making the problem simpler in some sense. And then not will lose is like a very similar function, right? Where what does it mean that not will lose? Well, it means that it doesn't matter where not will put its piece, X can still win. Right? And that's exactly what we do. So we try to put a not on every square. And then we're saying if the not goes there, but X will win with that possibility, then that means that that means that that means that so we're saying if X will not win with this possible move, then it's not true that not will lose. So if we find like one example where X will not win, then not will lose. So that's the basic kind of logic, right? So we try every possible location for the piece. And if logically that means that, well, for X will win, that that O will lose, then we return true. And vice versa, right? So that's the basic logic. And then why does it work? Well, because like mathematically it works out. Like it's true that if it's the case that there is a place where you can place the X such that O will lose, well, that means that X won. And that's what we're checking here. Right? It's like we're putting the X in every possible location and we find a position such that put the X there, then O will lose consequently, definitely, no matter what it does, then yeah, X has won. And then with O will lose, we're saying, well, if there is a way for, sorry, I'm not consistent here. So if there is a way to place a not on the board in such a way that it's not true that X will win, that it's not true that not will lose. On the other hand, if we checked every possible move by O and haven't found a situation where X will not win, well, that means that not will lose. Is that better?
Yeah.
Yeah, cool. Yeah.
Just in general, there's more kind of like you have to for your
No, not this year. Like I posted the first page. Yeah. So like what it says is what you'll get. Yeah. Yeah. No, like it's also like honestly, like so like it's not a rule this year anyway, but like I also like almost never actually apply it. So like I go and like so like basically like I don't want to like fail anyone who has a chance of succeeding in 190. So like regardless of like rule or no rule. So like if you're like close to 50, I look at your exam and I say like, and hopefully you're not in that situation anyway, but like I look at the exam and I say, okay, like, you know, like, is there a chance that this person will be successful in 190? And if the answer is yes, I bump people If the answer is no, like you don't want me to bump you up. Because like you're just like that's just asking for more trouble. And like I recognize that like sometimes like it's an exam, it's a stressful thing. So like I give people like a little bit of a benefit of a doubt. Honestly, kind of like the people fail are people who kind of, at least based on what they wrote, like have like basically never in their life written anything that actually ran. And like there are such people sometimes, like they would like not do the work in the lab and they did not do the projects. Like if that's not your situation, there's like you shouldn't be worried. You should not be worried. So that's at least kind of my, approach. Okay, are we all going to, oh, yeah.
Could you the question, I think, the last one?
Question 20. Sorry, which question?
Question 5, last.
Yeah. Yeah, okay. Yeah, so yeah, okay, we'll do it. So
Really good opportunity.
yeah. Yeah, okay. So what happens here? So here, like the n changes, the s stays the same. Right. So we call it with Sn. And then what happens? So we say 4-letter in S. So that means that there are multiple calls here. So how many calls there are? K length of S calls, exactly, yeah. Right. And then each call here, so this is n-1, and each call here again produces K calls individually. So how many calls in total are there? K squared, right? Because there are K calls here, and each one of them produces another K. So in total, you have K times K. Does that make sense? So then, okay, this is like n/2. They're all n/2. And each one of those, again, produces K. So over here, you have K cubed. And so on. How many levels? Well, you go down to 0. So this would be, so you start with k to the 0, then you go to k squared, k cubed, and you go from n down to 0. So that would be k to the power of n minus n plus sorry. You start from 0, so just k to the power of n actually. Right, so n plus 1 levels, and you start from k to the 0, 0 to n plus 1 levels. So each call here doesn't do any work, it just makes other calls. So each call takes a amount of time, so we just need to count the calls. So how many? Well, k to the 0 plus k to the 1 plus k to the n plus k to the n plus 1, and yeah, k to the n. So that's the geometric series. That's like this. So this term doesn't matter. K to the power of n plus 1 divided by k is k to the n. Oh, that's a good point. Yeah, that is actually an excellent point. So if you consider this to be not constant time, then you're in a bit, well, like you're in a bit of trouble. So here you're just, so here it's like not a lot. It just starts structuring is empty and letter is one. So here, yeah, thank you. That was a good point. So this is like actually K times how much this takes, and this takes like 2 or something, right? Because like you're creating a string of length 2 times like some C1. C1 here. So C1 is just a constant. And this would be times 3 times C, times 3 times C1. And this would be times 4 times C1 and so on. So that would be, so K to the 0 times 1. Two to this 1, 3K times 1, and so on. So what is this gonna be? 2 times 3 times n. So like this is still of K to the n. Give or take. Just because this grows slowly. So the way you can do it is you could say this is smaller or equal than this much, because you just say, well, this is smaller than n, and this is smaller than n, and this is smaller than n. So you can write it like that if you like. Yeah, that's actually a good point. Yeah, thank you. Yeah. Well, yeah. Okay. So just like a factor, like a factor of n here, and like you're right, like it's not like, negligible. Yeah. Say, I mean, we marked this as correct. Like honestly, I didn't remember this. I believe we marked this correct. Yeah. Like technically, like n times k to the n is larger, right? Because like n is not constant. Yeah. Thank you. Yeah.
The last one and the second.
Question 6. So the last one. So this one we had actually done, right? So this one is like the tree where it's n, and then you do work proportional to n, and then n minus 1, and you do work proportional to n minus 1 because you're creating a list of length n minus 1, and so on. So O of n squared. So we've done this example. This one?
Yes.
So what's going on here? So I smaller than n, and we're doing stuff. So that seems like it's proportional to n. And then we're saying, yeah. And then we're saying, while I is greater than 0, we're going down in steps of 2. So again, proportional to n, it's just that like we do n over 2 steps. So 2 things that are proportional to n together are also proportional to n. Indeed.
For that 9:30 edition.
No,